Welcome. Since we mentioned last time the implicit function theorem, I wanted to say something about the implicit function theorem and the project we worked on in 2008 with John Lesietre. We looked at the theorem of Neuberger, which is a nice implicit function theorem, a little bit stronger than the usual implicit function theorem. But first, a reminder, the implicit function theorem provides you some stability. If you have some function which has a root and the function is deformed, then and everything is nice, then there is still a root, as long as the derivative is not zero. Derivative is non-zero, so you can wiggle things a little bit and it still has a root. And one of the challenges we wanted to look at, that's 14 years ago, is whether there is kind of a more elementary proof of the fact that this functional equation has a smooth function f or small c. So that's a KAM problem for the standard map. So if you look at the standard map and Cherenkov standard map, and so for c equal to 0, you have an integrable situation, you have these invariant curves, and you can especially look at the invariant curve for Diophantine rotation number like the golden ratio, and then when you deform c, when you make c larger than 0, it still exists. This curve is there and it's analytic, and it breaks down around c equal to 0.9716, which has been well studied. There are lots of also physicists who have studied this connection with Lindstedt series, this connection with periodic orbits. There's a student here last year, Forrest Fletcher, has actually looked at this also in the context of neural networks, which is pretty cool. So they are called neural network optimizer to find invariant curves, and so so here there's a plot of these invariant curves for various things using the Newton method. So it's a very well-studied topic. The Cherenkov standard map is a famous prototype example, and it's related to a problem in statistical mechanics, the Frenkel-Kantorova model. So you can think about it also as a problem to kind of find solutions of a sequence of numbers. And if you look at that in that way, this is a Laplacian. This is a Laplacian of the lattice Z. And so if you look at the Laplacian here, and so you have a nonlinear perturbation of the Laplacian f equal to 0, which has solutions because the Laplacian has kernel. And so this is an interesting variational problem, and there are weak solutions. As Aubrey Mather theory, there's a lot of interesting mathematics involved. And especially his golden KM told us when it breaks down, there seems to be some universality. There is a kind of a fractal structure in the moment when it breaks up, and so on. So there are quite a lot of interesting things. So that's the standard implicit function theorem, which we also look at in calculus courses, like when we look at implicit equations of function of two variables, and then you can actually find the derivative, express the derivative if fy is not 0, and then you can find you can write down this level curve as a graph of a function. So that's where we see that in calculus. This is a standard situation also in multivariable calculus. And the proof is actually just writing down, integrating up that, and use the Picard existence theorem for differential equation, because this is bounded and smooth. If fy is not 0, there exists, you can integrate and you get g of x. And that works in full generality if you have a situation in Banach spaces. Like here, Banach spaces, for example, could be spaces of smooth functions, CR, or spaces of analytic functions, and so on. So this is a framework where you think you could use the implicit function theorem. There are hard implicit function theorems needed. It's scary, like this mask from the Swiss mountains. So it's a difficult situation, but the reason why this works is if you look at, for example, also here, you look at the operator, and with the golden ratio, any Diophantine, you can still invert it, but you lose some derivatives if you have, and then you have to smooth it out. You have to use a Newton method. That's what Nash and Moser kind of, Nash did it in a differential geometric setup, but then Moser kind of, extracted the functional analysis, and this has been refined by others. There's a nice article of Hamilton, which is called the hard implicit function theorem. There's also a book about the implicit function theorem by Kranz and Park. Maybe I display that book, where also the Nash-Moser implicit function theorem appears with proof. So one can see this using an implicit function theorem, but it's hard to do. And the question is, and just that's what we kind of proposed, whether there is not a kind of a simpler way to do that, kind of just using maybe a little bit harder implicit function theorems than the soft implicit function theorem, but still. And one of the things we tried is the Neuberger implicit function theorem. And John Neuberger had been here kind of a couple of times in the context of pedagogy, and we were interested in inquiry-based teaching, and I met him also in conferences in Denton and in Texas. He's from Texas. So, but the theorem is quite simple. You can prove it in a few lines, and the theorem kind of works also if the function f, which you're looking at, is not necessarily differentiable but only continuous, and then if some Gato derivatives, directional derivatives, exists. So in Banach spaces, this is different from the derivative. The existence of the derivative is called the Fresche derivative. This is a Gato derivative, and Gato is weaker, so that's just directional derivatives. And you don't even need the derivative. So if it's twice differentiable, it's actually enough that it exists in a dense set. And then you can try to do something like that using the inverse. You have an inverse using Fourier theory. You can write down an inverse matrix, and but this inverse matrix is explicitly invertible in the case when C is equal to 0. But when C is not equal to 0, this is a Toeplitz matrix, and this has been studied by mathematicians like Jean Bourgain. And the problem is that it's subtle. So even looking at the green functions is finite. If you take finite cutoffs and look at try to invert the matrices, this is subtle. And so we tried in a couple of frameworks, also in Siegel case. The Siegel case is a case which actually allows quite a reasonable proof, a proof you can do in classes. But Moser himself was the first who actually proved this twist map theorem. The proof is really hard, and it has been simplified by others, Ruissmann or Zehnder. Hermann was the first who had an explicit bound on the C, Michael Hermann. And then there were some Italian mathematicians who were at ETH when I was there, a grad student. They have a computer-assisted proof that they got 0.65, which is actually quite remarkably close to the bound which one believes is the threshold, 0.971. And there are others who have then looked at analytic cases. This is especially interesting when you look when do these series diverge? What is the radius of convergence? And so that kind of gives you already a hint about the breakdown value. But anyway, that's kind of a challenge. I'm not aware that anybody has written down a proof of this result, which can be taught maybe in 1 or 2 hours. Just, it looks simple, right? You might try to make a Taylor series or something like. Poincaré did and try to find some estimates here and do that in a reasonable way so that it can be done. But it seems to be just a hard problem. But let me just say something about this beautiful theorem of Neuberger, which is actually quite interesting also in, say, single variable or multivariable calculus. And it's something very clear in multivariable calculus, what happens when you have a function and you want to know that the function has a root. So you are away from, maybe you measure that, oh, you have that value, and what you want is you just want to be steep enough to get to within some neighborhood of the point you are looking at. You want to you want to assure that there is a root. Now the theorem just tells essentially if the steepness is big enough in that neighborhood, if there's always a direction you can go, Gato derivative, where you can go, so that you are going down enough, then you're reaching in that neighborhood, you reach a zero. So that's something which Neuberger used in PDEs, in partial differential equation, some Sobolev spaces or so. But let me just say something. I mentioned it already last time. So this is hard. This is the lattice C, and that's kind of the situation which we have here. If you replace the lattice C with a connection lattice, which is instead then the Laplacian is. So if you replace this with a Laplacian which is invertible, and the implicit function theorem applies, and you have for small enough C, you have actually the Fn equal to 0 is still a solution. So I call this the stability of the vacuum when you look at the situation on a connection, in a connection story. Okay, that's it for today.